Okay, so this is any real space Rn, this is any real space Rm, and we know that to map from this space to this space we use an m by n matrix. N is the number of columns in the matrix. It's the number of elements in every row, and of course if we have n elements in every row, that's going to allow us to multiply by a vector in Rn. And then we have m rows. Each row gives us a number in our new space. So if we have m rows, we're going to get vectors of length m when we do the transformation. Okay, so this picture is very similar to the one I drew before. It's just a little bigger, and I can point to more things, or at least maybe clarify things and generalize them to the bigger spaces, or potentially bigger spaces. We have the row space. Now we know what the row space is. We can reduce the matrix, and the number of rows with non-zero elements is going to be the dimension of the row space. And that's also going to be equal to the dimension of the column space, or what we call the image space here. And the row space maps directly to the image space, or the range, or the column space. We call it any of those things. Now we have, outside the row space, what do we have? We got the column space, we got the null space. Okay? If it's not in the row space, it maps to 0. So the null space maps onto the vector 0, which is in the image space. What about all this stuff out here that's not in the image space? Well, none of this stuff out here has a pre-image. Okay? Anything that has a pre-image has to be in here. So all this stuff is unaffected by the transformation. There's no vector outside of the image space, the column space, that comes from something over here. For any vector that's not in the image or column or range space, for any vector that's not in that space, there is no pre-image. There's no vector over here that maps onto it. The dimensions are, as we said, the dimensions of the row space and null space have to add up to the dimension of Rn. Okay, the row space has some dimension, the null space is a space, and these two spaces include all of Rn, so their dimensions add up to the dimension of Rn. Now, that's not really a proof. You got to do a little more than just say it in order to prove it, but you do need to understand that it's so, and you should understand how to prove it. Okay? And again, your range space or your column space has the same dimension as your row space. Okay, there's nothing here I haven't already said.